Hello there. Today we're going to talk about why we graph polar functions the way we do. To get an idea of why we graph polar functions, let's take a look at the following graph, 3 plus 2 cosine of x. In pre-cal, you learned how to graph these functions. Now, we're going to keep it really simple in here. We're not going over like those pi over 6s and things like that. So we're going to keep it simple. We're just going to graph the quadrantals. 0, pi over 2, pi, 3 pi over 2, and my favorite mathematical wrapper, 2 pi. If I plug in 0 into my function here, that's going to give me cosine of 0, which is 1. 2 times 1 is 2, so, and we add the 3, we're going to get a height of 5. We like the quadrantals because they didn't give us zeros or ones. For example, if I plug pi over 2 in, I get 0. So this just becomes a height of 3. Plug in pi over 2, cosine pi over 2 is negative 1, and that's going to give me a height of 1. And 3 pi over 2, that's going to be 0, so it's going to be a height of 3. And 2 pi, I'm back to where I started. And this is kind of what our function would look like last year in pre-cal. So the question is, well, how does this relate to polar graphs? So in red, let's go take a look in red. We'll graph the polar version of this. Now, a polar function is based on the angle. So we're going to, starting from the x-axis, we're going to measure our angle counterclockwise. Now, I know you've all seen these polar graphs with these little circles and everything on there, these little radial lines for angles. You don't need to have all of that to graph a polar function. All you need to know is the xy coordinate, and basically kind of like an idea. So if I'm at 0 degrees, so this is what it says. If I'm at x equals 0, I know my radius is going to be this over here. I know my distance is going to be 5. You might remember, for polars, we measure angles as r comma theta. So when we're going out, we're going to go out some radius and some angle theta. So when I'm on the x-axis, when x is 0, so if I look at the angle here, 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. Well, let's see what this kind of tells me. This is saying I'm at 0 radians, pi over 2 radians, pi radians, and 3 pi over 2 radians, and 2 pi radians. What does the y value represent? Well, the y value is the distance. How far away are we from the x-axis? So we can kind of think of this as the radius, r, which is the distance from the x-axis to the function itself, to the curve. Okay? So that's going to be our radius. So at 0 radians, my radius is 5. So I go out 5. As I move closer, at pi over 2 radians, my radius is 3. And I keep going, now my radius is 1. And then I'm back to radius of 3. And we remember how to graph these from last year. Let me make this a little bit better here. Ooh, messed that up. Get rid of the whole thing there. There, negative 3. So you might remember how to graph these from last year. This is going to be our limison. And there we have our function right here. But what I want to take a look here is the x-axis. If we, in polars, this little center part right here is called a pole. If we think of the x-axis as the pole, we are kind of bending, as you see, we are bending our function around that pole. And that's how we get our graph. And we can kind of see the relationship between the radius, or the distance of our y value, and our radius. So the y values of my rectangular function are is the radius of my polar graph. And we can kind of see that when we write out the equation in polar. In polar, this would be r equals 3 plus 2 cosine theta, where r is my radius, which kind of correlates to the y function. So let's take a look at another one. What would happen if we did a looped limacon? I want to show you this. This is y equals, what if we did 2 minus 3 cosine of x? Well, let's look at the graph of the function. And again, I'm only looking at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Again, this time though, if I let x be 0, we are at negative 1. It says cosine of 0 is 1, so we're going to be at negative 1 here. If we plug in pi over 2, we are at a height of 2. Let it be pi, cosine of pi is negative 1. That's going to put us at a height of 5, not on the scale. And here we kind of know the pattern, and it's going to go like this. Well, let's graph this in polar form then. Remember, in polar form, my x-axis is my, and I'm measuring my angles around, so we're starting at 0 radians, pi over 2 radians, pi radians, 3 pi over 2, and back to pi, or 2 pi in this case. So here we're starting at, we're graphing polars at 0 radians, we're at negative 1, so it's starting backwards here. Now, at pi over 2 though, it puts me at a radius of 2. But you got to be careful. See this area that's underneath here that's negative? Well, that's telling me we are looping. So that's going to kind of force us to make a loop like this. Whoops. There we go. There we go to that part. Now, at pi, my radius is 5. So if I'm facing pi, I'm going to go out 5 units. Whoops. I want to undo that. Let's do that. There we go. So I will be at 5 units. 3 pi over 2, I'm back at a radius of 2. And then at 2 pi, I'm back at, so if now I'm at 2 pi again, and I'm facing, didn't make my loop very well, backward like so. Now, the parts that are underneath the graph, we're going to talk about later on. This is an area problem for us. We have to subtract out those areas when we do areas of polars. But this little piece right in here represents the looped part. So the area underneath the graph, the area under is our loop. And that's how we get that looped limacon. Alright, so I'll see you guys later. We'll take a look at these real quick, okay? And I'll see y'all later. Bye-bye.